So welcome to today's session of the Discrete Math 2 course. Today we are going to look at further issues related to vector geometry, which is the topic we started last time around. I'll be drawing a few pictures, and the people who are with me in the lecture room today will solve some puzzles. And for those of you who are watching the lecture right now at home, or they will watch it at some point, whenever that point will be, please make sure you have pens and papers so that you can actually work through the examples that we will go through ourselves. And I hope that in the process today, as we introduce new topics, we'll also see some applications of linear algebra in real life, at least in the real life of a computer scientist. So let me start with some questions which are related to the topic that we were covering when we finished our previous course session last week. These are also questions for Dr. X, from Dr. X, in case you were wondering. They are just embedded in the course slides. So one thing that we were seeing last time was what happens when you multiply a vector by a scalar. And the scalar is a real number for us, but it could be anything that you can use to multiply a vector with. So we saw that if you take a vector and you multiply by a non-negative real number, what you're doing is essentially to scale the vector by the amount that you multiply it with. And since the amount is positive, you don't change the direction of the vector. If instead you multiply it by a negative real number, where you're still scaling the vector by the appropriate, by the absolute value of the number that you multiply it with, but you're changing the direction of the vector. Now, suppose that I give you a vector v in R2, so that's a vector in the Euclidean plane. What is this set over here? This set here is the set of all the scalar multiples of that vector v, but the multiplier is between 0 and 1. So it cannot be an arbitrary real number, but it's a real number between 0 and 1. So what do you think this set of points, this set of vectors corresponds to? So while you think, I'll take up our virtual drawing pad. So here's our R2, and so let's take a concrete example. Our vector could be, for instance, the one that corresponds to the point 1, 1. That's a point 1, 1 in the plane. So that's the vector v we are talking about in this specific example. Now, what happens if we multiply this vector by some quantity which is between 0 and 1? Okay, the vector will shrink. Well, unless you multiply by 1, in which case it stays the same. And we can make it shrink. We shrink both the, so we have some a in the interval 1, 0. If I multiply, if I take the vector a times v, I get the vector AA. Now, where is this vector going to lie? Is it going to be here? No way. Both the x and the y component are equal. It's going to be a shorter version of the vector. Well, if a is equal to 1, it's going to be the whole vector. But in general, it's going to be something like this. And in fact, if we multiply, if we choose our a to be 0, then we basically honey, we shrink the vector to the point, which is the origin. So basically, the set of points that we were looking at on the slide, namely the set of points of the form A times V, where V is our vector over there, where A is in between 1 and 0, this corresponds to all the points that you have on this segment here. These are all the points that you have between the origin and the point 1, 1, going up along the line that goes up 45, the segment that goes up 45 degrees. These are all the points that have the same x and y coordinate. So this is basically, this set is nothing but really the line segment between 0, 0 and 1, 1 that goes up 45 degrees. Any doubt about this? Now, what happens if instead I say, okay, sort of, let's take this set here. By now, I just take A could be an arbitrary real number. What is it that I'm describing? So I start from 1, 1. This is my vector V. That's the same vector that our running example. But whatever we say is going to work for any vector. But now sort of I let A range over the whole set of real numbers. So I can scale up the vector by any amount. So for instance, could I reach the point here, and let's say this point is 35, 35, drawing not to scale? Yeah, of course I can. I just need to multiply the vector 1, 1 by A equals 35. In fact, I could reach any point along the diagonal, no matter how far it goes. And since I can multiply also by a negative number, I can go the other way. So I can also go all the way down here. So what I'm describing with this set here, the green set, is a line. Is the line that goes through the origin and that goes up at 45 degrees. It goes up 45 degrees because I chose my original vector V to be 1, 1. If I choose a different vector, then the sort of the direction of the line would be, well, the direction that the vector I chosen gives me. So this vector here is often referred to as a direction vector for the line, or for a line. In this case, it's this line. If instead I had chosen, I had constrained my multiplier, my scalar A, to be non-negative, then I could have defined what people call a ray. The ray would be just, let me do it in blue. The ray would be just this one. The one that goes only up, but it doesn't go down. It's a ray because it has an origin and it's in infinite in one direction. Typically, a segment is something that has a beginning and an ending. It contains infinitely many points in between, typically, but it is bounded. Whereas a line is unbounded in both directions. So far, so good? Now, let's look at something which is related. So I have, again, my xy axis. And now I can take 2 points. These 2 points over here. Let me call them U and V. these 2 points. Now, if I ask you, suppose I define now this set where A and B are both between 1 and 0, and their sum is 1. Okay, so now, unlike before, I take 2 vectors. I don't take 1. I take 2 vectors, and I take all of their linear combinations. These are called linear combinations of the vectors u and b, just like when you were solving linear equations, each one of the equations of the equations corresponded to a linear combination of the variables. But now I take a and b, the 2 multiplying coefficients, to be in between 0 and 1, and their sum must be 1. What is it that what do you think I'm describing with this set of points? The question is, are u and v linear independent? Not necessarily. In fact, it doesn't really matter. So suppose I take A to be 1 and B to be 0. What do I get? Oh, there's something wrong with the broadcast. Thanks for letting me know. Yeah, okay.